A fundamental requirement to understand digital communication systems is analog to digital conversion. And the reason we need analog to digital conversion is because a computer can only process binary data. And almost all of the signals we encounter in real life from physical processes are analog in nature. For example, your voice, that's analog. Analog to digital conversion is defined in 3 steps. The first stage we have sampling. In the second stage we have quantization, and in the third stage we have encoding. In this video we will focus exclusively on sampling. Let's say we have a continuous time signal. If we take our continuous time signal, this, and we multiply it by a periodic pulse train, this spaced apart by an amount 1 over fs, which is known as the sampling interval, which is where fs is the sampling frequency, we get this result. Now, there's many reasons why we want this result, and they will be discussed in the future, but for now let's get an idea of what we are doing. So, more or less what we are doing is we are at this continuous time signal, we are taking samples that correspond to each sampling instant in our delta periodic pulse. So at Ts we are taking one sample, 2Ts we are taking a second sample, 3Ts we are taking a third sample, until we are left with this. And notice, this response is discrete. Now, this statement, this is mathematically equivalent to this. And this is very simple, right? We are just taking f of t and we are multiplying it by a periodic pulse train. And we will get this. Now, this is actually also equivalent to this statement. And in this statement all we did was we realized that this is not continuous. So see how we had f of t here? The only values that we have we add every n of ts. So for example, n is 1, n is 2, n is 3, right? So that's why we just replace t with this value here. And you'll notice here we had 9 results, right? 9 samples, or 9 delta functions, right? And that corresponds to 9 samples. So again, all we did was we took this signal and we sampled it by these pulses. That's all sampling is. Cool. Let's now discuss the sampling theorem. The sampling theorem claims that any signal that is band limited, meaning it has a finite bandwidth, can be recovered from its samples as long as we sample at a rate twice our highest frequency component. So if we have this response, this is just the exact same thing as this, right? We can reconstruct our original signal, from this, if we sample at a frequency twice higher than our highest frequency component. We should point out one thing here. This is only valid if you want to conserve frequency information. If you need to conserve information about the shape of a signal, you have to sample at higher rates. So, we should now understand why this sampling theorem works. So, say we have our original signal f of t. If we take the Fourier transform of this signal, we will get its response in the frequency domain. Let's assume our response is a triangular response like this. It corresponds to a single spectrum, right? Just a single triangle. However, our sampled signal, you remember we sampled this, right? This over here, if you take the Fourier transform of this, is modeled by this equation, we get an interesting result. The Fourier transform of a sampled spectra, of a sampled time domain signal, in the frequency domain, is replicas of the original spectrum. This is very, very, very powerful. And you'll notice that they are shifted by amount corresponding to our sampling frequency, right? So for each sample is shifted by Ws, our sampling frequency. Now, let's understand why this is actually working. Notice how here, in this case, we have WS greater than our highest frequency components, right? WS may comprise of an area like this, right? All the sampling theorem states is that if we sample at this rate, our what's it called, spectrums will be spaced apart nicely. And when they are spaced apart nicely, for example, this case, there's nothing in between here, right? Nothing's overlapping. When they're spaced apart, we can do this. We can recover our original signal using a low-pass filter. And this is a very, very easy thing to do. All you would have to do is match the parameters of your low-pass filter to meet the bandwidth of your signal. Now we should understand what happens when we sample at a rate lower than twice our highest frequency component. Before, if you remember, we had something like this, right? WS encompasses this range. But if we sample at a frequency lower, WS actually encompasses this range. So what happens is when we want when we are replicating our signal, we will get something like here. This area, it will overlap, right? And this is known as aliasing error. We do not want this. This is a very, very bad thing. It leads to distortion of system, and you cannot recover your signal. Okay, hopefully in the next video we'll discuss a practical example. So for maybe we'll find the range of permissible cutoff frequencies for our low-pass filter based upon the sampling theorem.